Mastering decentralization. Decentralization forces a drastic overhaul of system architecture and design, rewriting the future of infrastructure and applications. Why do the implications of decentralization on operational excellence necessitate a re-evaluation of the fundamental principles underlying system architecture and design, and what consequences will this have for the development of future infrastructure and applications? The implications of decentralization on operational excellence necessitate a re-evaluation of the fundamental principles underlying system architecture and design because decentralization introduces a paradigm shift in how systems are designed, deployed, and operated. In traditional, centralized systems, operational excellence is often achieved through top-down management, strict control, and predefined processes. However, decentralization disrupts this approach by introducing autonomous nodes, distributed decision-making, and peer-to-peer interactions. In decentralized systems, operational excellence cannot be achieved through traditional command and control structures. Instead, it requires a fundamental transformation of system architecture and design, focusing on autonomy, modularity, and adaptability. This re-evaluation of principles is necessary to accommodate the decentralized nature of the system, where individual components or nodes operate independently and make decisions based on local information. Firstly, decentralization necessitates a shift from monolithic to modular architecture. In centralized systems, a single, integrated platform is often designed to perform multiple functions. In contrast, decentralized systems require modular, loosely coupled components that can be developed, deployed, and updated independently. This modularity enables greater flexibility, scalability, and fault tolerance, as individual components can be modified or replaced without affecting the entire system. Secondly, decentralization demands a new approach to decision-making and control. In traditional systems, decision-making is centralized, and control is exercised through a hierarchical structure. In decentralized systems, decision-making is distributed among nodes, which must operate autonomously and make decisions based on local information. This requires advanced algorithms and protocols that enable nodes to coordinate and cooperate without centralized control. Thirdly, decentralization introduces new security and trust implications. In centralized systems, security is often ensured through perimeter defenses and access controls. In decentralized systems, security must be distributed and decentralized, with each node responsible for its own security and trust relationships. This requires novel approaches to identity management, access control, and data encryption. Finally, decentralization has significant implications for data management and analytics. In centralized systems, data is often aggregated and analyzed centrally. In decentralized systems, data is generated and processed at the edge, with nodes generating and consuming data independently. This requires advanced data management and analytics capabilities that can handle distributed, heterogeneous, and dynamic data flows. The consequences of this re-evaluation for the development of future infrastructure and applications will be far-reaching. First, decentralized infrastructure will become more prevalent, with applications and services built on top of decentralized networks and protocols. This will enable greater scalability, flexibility, and resilience, as well as new opportunities for innovation and entrepreneurship. Second, decentralized systems will require new skill sets and expertise, such as distributed systems design, cryptography, and decentralized governance. This will lead to the emergence of new professional profiles and training programs that focus on decentralized systems development and operations. Third, the development of decentralized systems will drive advancements in artificial intelligence, machine learning, and IoT technologies. Decentralized systems will require advanced AI and ML capabilities to enable autonomous decision-making, adaptive learning, and predictive analytics. Finally, decentralization will have significant societal and economic implications, enabling new forms of decentralized governance, community-driven innovation, and cooperative entrepreneurship. This will lead to the emergence of new social and economic structures, where decentralized systems and applications will become integral to our daily lives. In conclusion, the implications of decentralization on operational excellence necessitate a fundamental re-evaluation of the principles underlying system architecture and design. As decentralized systems become more prevalent, it is essential to rethink traditional approaches to system design, development, and operations. By embracing decentralization, we can unlock new opportunities for innovation, collaboration, and economic growth, and create a more resilient, adaptive, and equitable digital infrastructure for the future.